So B here, we have to prove this statement using mathematical induction here. So first things first, we're going to step number 1, where we say we need to show that this is true for n equals to 1. So here we say we need to show that this is true for n equals to 1 here. So to show that it is true for n equals to 1, we get this expression that we have of n here, we equate it to this expression on the right hand side, this side here. So we have n here is equal to n, open brackets, n plus 1 divided by 2 like this here. So then where this n here, we're going to substitute with 1. So we have 1 this side is equal to 1, open brackets, 1 plus 1 divided by 2 like this. So we have 1 here is equal to 1 multiplied by 2 divided by 2 here. So this gives us 1 is equal to 1 then. So therefore here we put a statement to say therefore true for n equal to 1 then. Then we'll go to step number 2 and just scroll down a bit. Okay, so step number 2 here is the inductive hypothesis. Okay, so on the inductive hypothesis here, we make an assumption where we assume that its groups for n equals to k here. So what we just do here on step number 2, we just get the expression the way it is, but then where there's n, we substitute with k. So this will be equal to k, open brackets, k plus 1 divided by 2 like this. So that is all that we're going to do on step number 2 here. So I go to step number 3, where we have to back our hypothesis and hypothesis that we have here, that this statement is also going to be true when n is equals to k plus 1. So meaning that we get the expression that we have, then we add a new term, and that term that we're adding, we call it the ak plus 1th term there. Okay, so then here we need to show that it's also true for n equal to k plus 1. So when we say n equal to k plus 1, this is the new term that we're going to add to the sequence that we already have here. So we have 1 plus 2 plus 3 plus k, then plus the new term now, k plus 1. Then on the right hand side, everywhere where there's n, we put k plus 1. So we have k plus 1, open brackets, we also have k plus 2 like this here. So let me just erase this. Sorry. Okay. So here we're saying we have k plus 1 plus 1 again. Then we divide everything by 2 like this here. So now, if you look at these terms here, starting from the first term that we have all the way up to the kth term, you notice to say that this is the claim that we made on step number 2, which is the inductive hypothesis. So we can just substitute where there are these terms here. We substitute with the right hand side of step number 2 there. So we're going to have k, open brackets, k plus 1 divided by 2 plus the ak plus 1 term here that we have, k plus 1 like this here, equal to, we have a k plus 1 and k plus 2 here divided by 2 like this here. So then here you'll notice that k plus 1 is common, so we can just factor out k plus 1. So when we factor out k plus 1 on the left hand side, we have our k plus 1 like this. Then here we remain with k plus 2. Then we divide by 2 there. So let me just scroll down a bit again. So here we are dividing by 2. This is equal to k plus 1 and k plus 2 divided by 2 there. So now what we have here, the left hand side is equal to the right hand side here. So now this shows to say that our sk plus the ak plus 1 term is equal to sk plus 1 like this here. So therefore, if this is the case that we have here, then this holds under mathematical induction. So let's just write a concluding statement on that. So I say that therefore this is true for n equal to k plus 1. So if it is true for n equals to k plus 1, then we say this holds so we say this holds under mathematical induction for every natural number and okay, let's go to the next question.